Hello everybody. Today I would like to continue our conversation about binary code and its relative function to computer, and how binary arithmetics could help us to work with understanding of how computer working. First of all, I would like to remind you a few things that I did in a previous session. Binary digits 1 or 0. Binary digits 1 or 0. Only 1 or 0 because it's associated with yes and no, right and left, and up and down, but most interesting with on and off. Why it's most interesting with on and off? Because, folks, on and off, it's relationship to the electrical circuit. So if we go for battery connected plus minus to the electrical contour, and we'll use the switch and we'll connect the switch to the lamp. So now the contour is open. The contour is created in such way so electrical current doesn't have possibility to run. But if we push the switch down, the electrical current will go through the circuit and the light will be on. So this is event like yes and no in human relationship, but this is on and off in computer relationship. Folks, speaking about binary arithmetics and binary digits, I would like to imagine that most important thing for the computer is to transmit information that is relative to human understanding. But human understands letters like A, B, C, D, or small a, B, C, D, and then numbers 1, 2, 3, 4, and so on. And punctuation is dot, semicolon, colon, equal sign, root sign, and so on. Mathematical symbols and everything else. So folks, I'll tell you that this is set of symbols which is 256 each other. 256 symbols. But I need to use binary code to represent this on the computer. But I so far have only 2 digits. 1 bit can represent either 0 or 1. So what can I do? Using these 2 digits, I can use only 2 letters, A and B, because I have only 2 events. The bits equal 0, the bit equal 1. But what's happened if I use 2-bit? 2-bit. 2-bit will give me, by the way, it looks like 2 placeholders. Each placeholder could be 0, 1. So I can use 0, 0, 0, 1, 1, 0, and 1, 1. This is already 4 variations. 4 variations. And each variation is unique, so I can use it to represent different alphabetical letters. So A, B, C, and D. But that is not enough, definitely. So what can I do in this case? How can I make more letters? Definitely I can use 3-bit. 3-bit, folks, either 3 placeholders like this, and that will be 8 combinations. I would like to sharpen your attention that every time we add 1 bit, that will be 2 multiplication by 2, so it will be doubled. So if this is 4 variations, so for 3-bit that will be 8 variations. Let's see them. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. These 8 variations will be able to represent 8 letters: A, B, C, D, E, F, G, and H. But this is not enough. We need to have 256 variations. 256 variations. Let's see how many variations for 4 bits. 4 bit. We talk about the doubled number of variations. I don't want to write variations as they are, but I can say that will be 16 variations for 16 letters. That is not enough. For 5 bit, that will be doubled, 32 variations. Not enough for 256 symbols. 6 bit will have 64 variations. 7 bit will give you 128 variations, and 8 bit eventually will create 256 variations. 256 variations, folks, is enough to represent each symbol. But 8 bit is informational unit that have name, and this name is 1 byte. 1 byte is equal 8 bit. How 1 byte looks like? This is a table with 8 placeholders. Each placeholder could have a value either 0 or 1. So if I take all zeros, that will be byte. If I take all ones, that will be another byte. If I take some zeros, some ones, that will be another byte. So let's see like this: 0, 0, 0, 1, 0, 0, 0, 1. And this is a byte. So total number of different bytes is 256. But folks, every single line of this code of 1 byte variation will belong to a certain letter. This one to letter A. For example, this one to letter B. This one to letter C. And so on and so on. Totally 256 variations. Folks, to calculate number of variations if we have number of bit is easy. The formula is like this: Q, number of variations, is equal to in the power of n, where n is equal number of bit. Typical question: if I have not 1 byte but some kind of set of binary digits which is 9 bit, how many variations it will be? It's not difficult to calculate. Q for 9 bit will be 2 in the power of 9. If you take calculation, that will be 512. 512 variations. Folks, this code table that represents all English language, are basically language based on English in binary code, is standard in the United States and actually standard in entire world, and named ASCII code. It's ASCII, meaning American Standard Code for Informational Interchange. ASCII code, and this is American Standard. And this code actually produced 8 bit per character. So number of code lines is 256. Its number of code lines. And this code is pretty standard for transmitting letters. So folks, if you have a keyboard, let's say this is key A, that will be key S, that is key D, and so on. And this is KB, keyboard. So keyboard connected to computer with 8 wires. 1, 2, 3, 4, 5, 6, 7, 8. Let me continue them. This is 8 wires for connection of keyboard to the computer. Why 8 wires, folks? Because when you push letter A, this code, when you see it, ASCII code, will be sent to the computer. It will be sent to the computer. Every time you touch different key on the keyboard, different set of zeros and ones, totally 8-bit, will be transmitted from keyboard to the computer. Computer actually tuned up to understand ASCII code and converted to the printable or visible letters. So ASCII code is good to transmit from any digital source to the computer. But question is, we have different languages. We have, let's say, Chinese language, which utilized kind of symbols like this, hieroglyphs. We have Arabics alphabet. We have Greek, something like this, and something like this. Greek language. We have Russian with Cyrillic symbols like this, and this is different. And it's total more than 56,000 symbols in the planet Earth. What we can do if we need to transmit all of these symbols for international. So let us continue. We spoke about different alphabetical characters that actually different languages can be needed to represent in the code, because computer, when you connect to internet, computer must have ability to encode different symbols, but they actually going out from the limit of 256. So what we're supposed to do? How can we dissolve this problem? So people find the way to dissolve it. That will be new encoding system. New encoding system named Unicode. Unicode. So Unicode is encoding system with 2 bytes per character. 2 bytes per character. Then I will use this table to show you 1 byte and then another byte. Now we need to calculate. This is placeholders for binary digits. So now question, how many symbols can we represent with 2-byte system of encoding? We have the formula. Q is equal to 2 in the power of n, like this one. Q is equal to 2 in the power of n. So let's calculate Q for 16-bit. That will be 2 in the power of 16. If you take calculator, you will see that it is 256 multiplied by 256. That will be 65,532. It's approximately. I don't remember exactly, but it's more than 65,000 combinations, folks, variations. So this number of variations could be fitted to any of the language that could be found on the planet Earth. So Unicode is good for internet because internet is international network. So folks, in this case we can see that digital binary code could be suitable to represent alphanumeric information, with that meaning alphabetical enumeration and punctuation on the computer. Definitely inside of the computer it's in a binary code, because inside of the computer we have only circuitry that actually either have current inside or do not have current inside. These circuits could be inside of microchips or transistors that actually computer filled with. Now, let me tell you folks about units that we use, bits and byte. Bit is elementary unit for taking choice between left and right, up and down, on and off. So 8 bit is equal 1 byte. 8 bit is equal 1 byte. Now, 1000 byte. Folks, 1000 byte is 1000 letters. 1000 byte is equal 1 kilobyte. 1 kilobyte. And 1000 is 10 in the power of 3. And that is 1 KB. 1 kilobyte. 1000 is kilobyte. Then, folks, 1 million, 10 in the power of 6. That is million, which is 1 million is equal 1 MB. 1 megabyte. 1 megabyte. Folks, gigabyte, 10 in the power of 9. That is 1 billion. Billion bytes. That is 1 gigabyte. Gigabyte. And 10 in the power of 12. That is 1 terabyte. Or 1 TB. 1 TB, terabyte. Folks, every byte from this kilo, mega, giga, or tera, every byte is responsible for one letter in the alphanumeric code. Alphanumeric code. Now, let me introduce the typical question on that you can find, problem that you can find in exams. Let's say I'll put it in a frame here. Let's say the book of Bible contain about 48 million letters. 48 million letters. When Bible was digitized and saved as a file, what is the size of the file? How to approach this problem? 48 million letters is good to encode with ASCII code, and ASCII code, if you can see here, 8 bit per character. So 1 byte per character. So it's 48 million bytes. As soon as 1 million is 1 megabyte, so 48 million will be 48 megabyte. 48 megabyte, folks, which pretty small file, because your flash drive could be few terabytes now. But this is when encoding system is ASCII code. ASCII code because 1 byte per character. But what if we use Unicode? Folks, Unicode must be represented 2 bytes per character. So for Unicode, we need to multiply it by 2, and that will be 96 megabyte. Because in Unicode, let's say Bible in Chinese language, that will be 96 megabyte, because Unicode is 2 byte per character. So everything I spoke about these 20 minutes is that we can actually use binary code to represent alphanumeric information on the computer, which is very important because computer is instrument to have access to the human assets, to the libraries, to books, to documents, and many things that use alphanumeric information. But next question, computer can calculate, but how? how computer can use numbers and digits to make calculations. Before we go to the binary calculations, folks, I would like to make you understand how decimal calculations is developed by human civilization. Before everything, we didn't know any numbers like 1, 2, 3, 4, 5, 6, and so on, but numbers were Roman numbers: 1, 2, 3, very primitive, 4, 5, 10, 12, 100, and so on. These numbers are probably beautiful concerning glyphs. By the way, glyph is the way how they looks like. Glyph, for example, for letter A, could be glyph like this, and glyph like this, and glyph like this. It looks like glyph. Glyph. The way how this number or letter looks like. So they're beautiful on the dial in a Grand Central, but you cannot, for example, multiply 112 at least by 4. It is impossible to calculate. But revolution in this matter was done by Asian genius mathematician whose name was Al-Khwarizmi. Al-Khwarizmi. He was the wizard who lived in contemporary Uzbekistan in the Middle Asia, and he made a pilgrimage to the Asian India. India actually was very good in mathematics, much better than Asia and Europe at this time. And when he came to India, he was surprised that Indian people, they use a different way to record the numbers. And numbers were like this. They use geometry. 1. Why 1 is this? Because the angle is only 1. 2. 2 angles. 2 sharp angles. 3. You can see 1, 2, 3. 4. 1, 2, 3, 4. 5. 1, 2, 3, 4, 5. 6, folks. 1, 2, 3, 4, 5, 6. Now, my teacher asked me to write 7 like this. And now I understood why 7 is like this. 7 is like this. 1, 2, 3, 4, 5, 6, 7. 8. Definitely 1, 2, 3, 4, 5, 6, 7, 8. 9, folks. 9 is like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. And 0. 0 is round. There is no angles inside. So that is 0, 0 angles. Then, folks, these glyphs now named Arabic. Arabic. Because Al-Khwarizmi was actually Arab. And he spoke Arabic language. And he wrote the book named Al-Jabr wa al-Muqabala. This is from Arabic language, meaning algebra, al-Jabr, al-Jabr. So he was a person who established the algebra in mathematical sense. Now, he opened for normal people how to make mathematical equation. So let's go for any number like this. $275. We have 275 and that's it. But folks, when you open the idea what is 275, you will be able to figure out that 200 bills plus 7 10 bills plus 5 singles. So for the market, for the stores, that is very important that first we have the harder, the more weighty, the more heavy number to hundreds. And then we have tens, then we have singles. So basically we can figure out that 100 is 10 in the power of 2, 10 is 10 in the power of 1, and 1 is 10 in the power of 0. Any number in the power of 0 is equal 1. This is about algebra. So folks, can I re-record this like this? That will be 2 multiplied by 10 in the power of 2 plus 7 multiplied by 10 in the power of 1, plus 5 multiplied by 10 in the power of 0. So definitely this is 200, this is 70, and this is 5. But folks, this 0, 1, and 2 power of the 10, because 10 is a basis of a numeric system, because we have 10 fingers. 10 named decade. This is 10. From this word decade, from the Roman decimus, meaning 10, this system named decimal. Decimal system. Not like Roman system. In decimal system, positions 0, 1, and 2, and more, 3, 4, 5, depending on how many digits we have in the record of quantity, but this is record of quantity of money we have. So this situation could be assigned as a position of numbers. Position 0, position 1, and position 2. So as soon as positions are hardly assigned, this system named positional. Now let's review another sample. Number of money, quantity of money will be $5,034. $5,034. Alright, so how to understand the structure of this record of quantity? First of all, we need to mark up the positions. Position 0, position 1, position 2, position 3. And then I would like to make the same polynomial opening. That will be 5 by 10 in the power of 3. Why 5? Because 5 corresponding to this 5. And the power of 3 is power of position. 3 and 3. Plus, this is multiplication symbol. Plus 0 multiplied by 10 in the power of 2. Plus 3 multiplied by 3 by 10 in the power of 1. Plus 4 multiplied by 10 in the power of 0. Now can we calculate it? This is 5,000. This is 0, because multiplication by 0 gives you 0. This is 30, and this is 4. When you summarize this piece, you find exactly 5,034. 0 we just missing. We don't need to pronounce it. So folks, then I would like to introduce the rule. The rule is certain. The highest digit that we use here is 9. Digit. Because single digits, the highest one, the maximum one is 9. But if you add 1 to this 9, you will have 1 that will be being carried to another column. That will be carrying, and that will be 1, 0. That is rules for the addition, folks, which actually works with multiplication and other action in arithmetic. Let's remember that. Now, but that is very good when we're doing it manually or with calculation, with electronic calculator, which actually operates with these numbers. But what about computer, folks? Computer operates only with binary codes. So what we can do? Let's see. Let me take any amount, consider that money or whatever amount of something, each other. And then I'll put 1, 0, 0, 1, 1, 1. And that will be binary. That is decimal, and that is binary. Can I do the same thing here? Yes, I do. Yes, I can. But take a look, folks. Here I multiplied by 10 because I have 10 digits. But in binary system I have only 2 digits, 1 and 0. So what I need to do? I need to put positions first. 0, 1, 2, 3, 4, and 5. Position 5 will generate me something like this. 1 multiplied by 2 in the power of 5. 2 because it's only 2 digits, 0 and 1. It's binary, meaning binar, meaning binary, meaning by, that's 2. 2 in the power of 5 plus 0 multiplied by 2 in the power of 4 plus 0 multiplied by 2 in the power of 3 plus 1 multiplied by 2 in the power of 2 plus 1 multiplied by 2 in the power of 1 plus 1 multiplied by 2 in the power of 0. Let's calculate. 2 in the power of 5, 2 by 2, 4, by 2, 8, by 2, 16, by 2, 32. So that is 32 in decimal. This is 0, this is 0, this is 2 square is 4, 2 in the power of 1 is 2, and 2 in the power of 0 is 1. So let me calculate. 4 and 2, 6, 7, 32 and 7 will be 39. Folks, I can do quantity in decimal with a record in binary. Let's try another one. 1, 0, 1. How much is this? Binary. Positions 0, 1, 2. 1 multiplied by 2 in the power of 2 plus 0 multiplied by 2 in the power of 1 plus 1 multiplied by 2 in the power of 0. 2 square 4, this is 0, and this is 1. So totally this is 5. 5 in decimal. But folks, if we have this rule, the highest digit plus 1 is 1, 0, this is not 10. This is 1, 0. We call it 10, but this is 1, 0 because 1 going from carrying to another column. So I can make another rule for binary system, which is highest is 1 plus 1 will be 1, 0. And that is rule for binary code. You can ask me how that can be. 1 plus 1 will be 1, 0. But folks, 1, 0 is binary. 1, 0 is binary is, let's calculate. 1, 0, how much of this? Position 0, position 1, that will be 1 by 2 in the power of 1 plus 0 multiplied by 2 in the power of 0. This is 0 and this is 2. So 1 and 1 is 2 in decimal, but in binary 2 is 1, 0. Don't forget this. Binary 1, 0 is equal to decimal. Now, if I have 1, 0, 1, and I would like to add 1, 1, 0, 1 plus 1, as soon as this is 5, when I add 1, that's supposed to be 6. Let's go for this. 1 plus 1 will be 0 writing, 1 carrying, according to this rule. 1 plus 0 will be 1, and 1 is going down from the top. 1, 1, 0 binary. How much of this? 1, 1, 0. Positions. 0, 1, 2. That will be 1 by 2 in the power of 2 plus 1 by 2 in the power of 1 plus 0 by 2 in the power of 0. This is 0, this is 2, and this is 4. 4 plus 2 will be 6. Folks, look what we did. We just proved that arithmetical action like addition, when we add 1 to 101, it gives you 110, which is 6 in decimal. That is absolutely incredible resume from these calculations. For that meaning, that result of the arithmetical action, of arithmetical formula or equation being substituted with binary digits is not dependent of what system we use for calculation, binary or decimal. In both systems we will have the same result. So what does meaning, folks? What does it mean? This is meaning that we can use computer for calculations. But what we need to do? We need to have instrument in the computer which is allowing to convert decimal to binary. Then computer will calculate everything as binary code in binary system. Then it will convert binary into decimal, and then you can see the result of calculation immediately on the screen. That is how computer and calculator works. When you input your data into calculator, that will be inputted as decimal, but as soon as you put decimal numbers, that will be converted immediately to binary. Then internal processor unit will process arithmetical and algebraic calculation and then immediately give you binary result, which is equal result in decimal system when it will be converted. So folks, that is all for today, what I would like to tell you about how computer can represent alphanumeric information and then how computer can calculate. Definitely, if we can make addition, we can make subtraction the same way, we can make multiplication and division and all other calculation that algebra and calculus involved. So, thank you for your attention.